Okay. Make this bigger. Okay, so today I actually have some slides for a change. And so what is the plan? Let me first start with the bigger picture. The plan is to do rigid body physics. And we will do it like this. So today I will cover rigid body kinematics and quaternions. Well, not that much of kinematics. More about quaternions. And next week I'll be gone, but Robin will be here. It's our visitor from Germany, so you can learn some quality German engineering in terms of rigid body physics. So he will take the next 3 classes. I won't be back until next Tuesday. So. And we are planning to do some homework on rigid body physics. We haven't quite done it yet, so we will keep you posted. We still first have to cover the basic material, but then we are planning to do some new homework on that. Something that wasn't there the last year. Is that okay? Okay, so let's get started with rigid body stuff. So I guess maybe I could introduce it by why is rigid body physics so popular? You can, if you open up pretty much any game, or at least most of the popular games, you will find there's some element of rigid body physics, right? I was like showing things like Angry Bird type of games, or even 3D, both 2D and 3D games. They have some physics simulation, right? I think that was the first application of physics-based simulation that really made it mainstream into games, rigid body physics, right? And what do you think is the reason for that? Might have mentioned that in the very first class briefly, but today we'll go into more detail. Why rigid bodies? Like rigid bodies, first of all, they are an abstraction, right? There is no such thing as a rigid body in the real world. Why is that, by the way? If you think about it, it's sort of funny. If you have a rigid, you have a, no? Well, yeah, you have an idea?
Everything is deformable.
To some extent,
yeah,
right?
Enough force, like
Exactly. It will deform or will break eventually, right? But even the very idea for the rigid body basically is something that will not possibly change its shape, right? If you think about it, that would mean that information could actually travel faster than speed of light, right? Because if you like pull on one end of the rigid body and the other end would immediately move, right? So that actually violates the very elementary physical principle. So that's an abstraction. It's totally cool abstraction for many physics-based models, and it's absolutely cool for like the games or physics-based animation. That's what we are covering here. But why is it so practical? Why people like it so much, as opposed to like deformable objects? So everything in the real world, many things are quite deformable, right? Like human bodies, clothes, and stuff. It's simple. That's exactly the reason, and it's computationally simple, right? Because a rigid body, and that's what I want to start with. So if I have a rigid body, the state of a rigid body, the kinematic state of a rigid body, that can be described by 6 degrees of freedom, right? 3 degrees of freedom for translation, or position of the center of mass, and 3 for rotation. So I assume we are in 3-dimensional Euclidean space, R3, right? You could be also doing rigid body physics in 2 dimensions, but then the things only become easier, so we can as well explain everything in 3D. And if you want to do a 2D rigid body engine, you will have an easier time. So I think it's obvious why we have 3 degrees of freedom for translation, right? Because you have axes X, Y, and Z. So there's nothing special about it, and everything is linear as long as translations are concerned, right? So that's the easy part. The rotations, that's the hard part, or not super hard, but a little bit trickier part, and that's essentially what this lecture is about. That's what will lead us to quaternions. So let's start by clarifying why is it 3 degrees of freedom for rotation. I think that's much less clear than in the translation case, right? You cannot just argue by dimensions because already in 2D that would not work, right? If you were in 2D, what is the dimensionality of rotations? What is the degrees of freedom for rotation? Just 1, right? So clearly it's not exactly related to the dimension, right? So why is it 3? There's more. Right. That's one argument you can make. So the argument you are making there is, I think, the Euler rotation theorem or whatever it's called. That says that every 3D rotation can be decomposed into 3 elementary rotations, and from that it's obvious that you have 3 degrees of freedom. If you wanted to make like an elementary linear algebra argument, you can do it like this. So the standard way how do we represent rotation is using a matrix, right? You all know this. You all took some graphics class. So we have a 3x3 matrix M. And we say that the matrix M is a rotation. So does everybody know the SO3, the fancy formalism for rotations? The SO3 means special orthogonal group in 3 dimensions, and that's the group of 3D rotations, okay? The fact it's mathematically grouped, that means that there's identity, invert element, and you can multiply. I don't want to go
special orthogonal. Right?
Special orthogonal, yeah, and I'll explain that in a second. So a 3x3 real matrix is in the special orthogonal group if and only if. So first of all, it has to be orthogonal. So MTM is identity. So that would be orthogonal so far. That would be O3 group, and we also require that the determinant of M is 1. Okay. If you remember some basic linear algebra, then from this you can this already implies that the determinant is plus or minus 1. So by this constraint, but this additional condition, we just rule out the case of minus 1. So we require the determinant be plus 1. Okay? Everybody follows that? You know, I don't know how much detail do I need to go. If you just use the product rule for determinants, the determinant MT is determinant M, you immediately see the determinant M must be plus or minus 1. We don't want minus 1 because, okay, let me just say this. What would the transformation be if we had determinant minus 1? If it was an orthogonal transformation, determinant minus 1, how do we call it? Mirror or reflection. Yes, it would be mirror transformation. So that's clearly not a valid rotation, right? Because rotation is something that a rigid body like this pen can do, but reflection does things like this, right? If I have a rigid body like this, okay, that's not the most beautiful one, but it will do. Let me make a chimney here to make it clear. Reflection does this, right? That reflection like turns right-handed glove into left-handed glove. That's not something you can do to a rigid body without like destroying him in the middle or something like that. Okay, and from here you can see you can see another reason why this is 3 degrees of freedom for rotation. Because, so the matrix starts with 9 degrees of freedom, right? 3x3 is 9 degrees of freedom, okay? And if you look at this, how many constraints do we have there? Well, if I write the matrix like this, column M1, M2, M3, so how many constraints are contained in this matrix equality? Should be an easy answer.
Are you saying for the columns or?
So this is in general. This is a matrix equality, right? I have some matrix on the left-hand side. I have some matrix on the right-hand side. They are both 3x3 matrices. I assume that's obvious. I could also make it more explicit by saying this is I3. So how many constraints do we have there? Well, correct. That's the, yeah. So the ones that are linearly independent are like this. So we want all of the columns to be orthonormal, right? I'll just write it really explicitly here. So that's the orthogonality of the columns. And then we also want that the norms, that they are actually orthonormal vectors, that the length of each of the columns is 1, okay? So this is 6 constraints we have there. Okay, so what we get, we have 9 degrees of freedom minus 6 constraints. That gives us 3 degrees of freedom for rotation. That's another like elementary argument you can make. But the one with the Euler theorem is also fine. If you already know that every 3 rotation can be decomposed into the 3 rotations about the coordinate axis. Does that make sense? So usually you would represent rotation by a rotation matrix, right? But from this discussion you can see it's a little bit wasteful, because what you are doing if you have a rotation matrix, you are using 9 degrees of freedom, like 9 floats or doubles, and 6 of them basically are redundant, right? You only need 3, really. So this is a little bit redundant representation, right? So you might be thinking, why don't we just use 3 parameters to represent rotations? Like, for example, Euler angles, right? That's certainly, you certainly cannot go below 3, but you can do 3 Euler angles. Do you know what is the problem with that? Yes, there is the gimbal lock problem. I don't want to go into too much detail, but there is some interesting stories around it. It's basically, the problem is that of singularity. It's easier to explain on just 3D sphere. So imagine a sphere in 3D. There is no way you can cut it open and parameterize it onto a plane without creating a singularity somewhere. In the case of rotations, in the case of SO3, this is known, or the Euler angle, this is known as gimbal lock. There have been some interesting stories to it. They had this problem on Apollo 11 when they were landing, and there was a sentence, "Give me a Ford gimbal for Christmas." So that's the problem of a singularity. And there is a way to prove that just using 3 degrees of freedom, no matter what parameterization for rotations you will use, will never be able to get around the singularity. And it turns out if you want to have a singularity-free parameterization of 3 rotations, you have to have at least 4 degrees of freedom. And that's exactly what quaternions are. So quaternions, they use 4 degrees of freedom. They can represent any 3D rotation, as I will explain in a little bit. And because there is 4 degrees of freedom, there of course must be one constraint. So we get back to our 3 degrees of freedom. Okay, so let me just put this in perspective. So quaternions, as opposed to matrices would have 9 degrees of freedom and 6 constraints. Quaternions have 4 degrees of freedom and 1 constraint. So already here you can quite clearly see that quaternions are a more efficient way to represent rotations. It's also slightly different. There are also some other differences between quaternions and matrices, which we'll get to in a minute. You've probably all heard about quaternions a little bit, right? Because that's now a standard part of computer graphics. Have you also heard the story about the guy who introduced quaternions to computer graphics? That Steve or Norm told you. So, the guy who introduced quaternions in computer graphics was Ken Shoemake in his seminal 1985 SIGGRAPH paper, Animating Rotation with Quaternion Curves. It's a very good paper, by the way. Also gives you the explicit formulas how to convert from matrix to quaternion and back, and so on. And I think this paper really introduced quaternions to computer graphics, and everybody's has been using it since then. And why I'm bringing this up, the Ken Shoemake, if you look at his later paper, you can see an interesting affiliation of him. He was a PhD student here at Penn, at the graphics lab here, way before my time. I was alive, but I was far away. And the interesting story is that he was a PhD student and he was fired. He didn't pass one of the exams. And so no doubt he was a whimsical character, but he was a genius. So because he had this seminal work that really changed the way computer graphics is done, at least some parts of computer graphics. But he got very bitter, and then I don't know what he's doing now, but it's nothing related to computer graphics. So, yeah. So I guess that was a sad story. Let's take a look at a more happier story. So there is another story today. It's all about stories. There's a story of Quaternions. So Quaternions were discovered more than 150 years ago by an Irish mathematician called William Rowan Hamilton. And it took about 15 years, I think, the mathematicians were looking for a generalization of complex numbers. They were all excited about complex numbers and wondering what is beyond complex numbers. And they were looking for things that had like 3 degrees of freedom. Complex numbers, they give you 2 degrees of freedom. Like you have real numbers, that's 1. Then complex numbers, they have 2. And clearly they were asking, is there some interesting algebra which would have 3 degrees of freedom? And they couldn't find anything. Until Hamilton had this ingenious idea that we actually need 4 to be able to get an algebra with reasonable properties. And the story is that he had this idea that we need the 4th unit while he was walking across a bridge in Dublin, in Ireland, with his wife, actually. Still thinking about Quaternions. And he was so thrilled by his discovery that he carved this Quaternion multiplication formula on the stone of that bridge. And I used to live in Dublin some time ago, so I took a trip to the Quaternion Bridge, and I found there is still a memorial plaque on the bridge. So the original engraving is probably not there, but there is a memorial plaque which is here, and it has the Quaternion multiplication formulas on it. So the Quaternion multiplication formulas are like this: I squared, j squared, k squared equals I, j, k is minus 1. So what are these j and k guys? The I is exactly the same as you know from complex numbers. Okay, that's the I squared equals minus 1. Everybody knows that, right? And j and k, those are just 2 other imaginary numbers. They, just like the complex unit, j squared and k squared, they are also minus 1. But then the whole idea is how do they multiply together, right? If you, from this, you can actually derive everything. So you can, for example, derive that ij equals k. If you do ji, you will get minus k. One way, if you want to remember it, a nice way to remember it is to remember this diagram. I goes to j, that goes to k, that goes to I. So if you do I times j, will get k. If you go the other way around, j times I will get minus k. Similarly, j times k would be I, and so on. Like, algebra is beautiful because it's all about symmetry, so how these things create these patterns. Okay. Yeah, and Quaternion, as I said, they have 4 degrees of freedom. So there's w, x, y, and z. Those would be real numbers. Those would be the parameters. And the I, j, and k, those are some imaginary numbers. Okay. And now the fun starts. So now we can actually be computing with it, because Quaternions form an algebra with a multiplication operation, which is quite amazing. So let's take a look at that. So the first thing we can do, we can split a Quaternion into a scalar part and a vector part, or purely imaginary part, if you will. That's just the same like you do in complex numbers, right? You have a scalar part and purely complex, or whatever it's called, or imaginary part. So we can do the same thing in Quaternions. So because this is just 3 degrees of freedom, this vector part, this R0, so I can just say the R0, I can basically look at it as a 3D vector. Okay, I can sort of think about it as an element of R3, right? Because, or I can identify with an R3, an X0, Y0, Z0, okay? And one way you can work out the Quaternion multiplication is exactly according to these rules. So if you actually do this, if you take one Quaternion Q0, another Q1, so the same notation, scalar part and vector part, and if you carry out the multiplication, so it's a little bit tedious, I'm not going to do that. You can do that for homework if you want. You just apply distributivity and you just apply these rules. So I squared will be minus 1 and so on. And what you get at the end is a very interesting expression. So this is a Quaternion multiplication of 2 Quaternions, Q0 and Q1. And it turns out that the scalar part of it will be this, W0, W1. So W0, W1, they are scalars, so this is just a scalar multiplication. R0 and R1, we are looking at them as 3-dimensional vectors, and this notation, this means a dot product, okay? This is a dot product. I guess to be more consistent with my previous lectures, I should probably denote it like this. It would be equivalent to that. But this is like an older-fashioned notation for dot product. So all this is a scalar, and that's the new scalar part. That's the scalar part of the product. This should be just a scalar product. I don't know why do I have this cross here, because this is a scalar vector product, okay? And here, this is an interesting thing. Here, this X is an actual cross product, 3D cross product. So everybody knows what a cross product is, right, in 3D. So the multiplication, Quaternion multiplication, so this is the scalar part, this is the vector part, this whole thing. All of these things are 3D vectors, right? Cross product also produces you a 3D vector. So the Quaternion multiplication actually mixes all products we know. Scalar product, dot product, and cross product. Okay? And you don't have to stop here. You can actually be generalizing. You can go beyond Quaternions. There is more than that known as Clifford or geometric algebras. And they basically generalize these ideas to higher dimensions. But let's not go there. Let's just stay with Quaternions. So Quaternion multiplication, and the multiplication, that's what makes it an algebra. That's what actually makes it different from some like arbitrarily defined operation. So the one important property is that it's associative. In case you don't remember what that means that if I do first Q0 and Q1 and then multiply with Q2, I'll get exactly the same thing as if I do first Q0 and then Q1 and Q2. That's associativity. What we lose by going from complex numbers to Quaternions is we lose commutativity. It's no longer true in general that Q0, Q1 would have to be equal to Q1, Q0. Happens sometimes, but doesn't happen always. So in general, it's not commutative. And the other thing that will be useful later, we can also think about Quaternions as 4D vectors, right? They're just 4 degrees of freedom, W, X, Y, Z. So I can just imagine it as a 4D vector, and I can just define dot product on it. Just like on 4-dimensional vectors, dot product, nothing special. So I will just denote it like this. Okay? So here are some basic operations we can do with Quaternions. What I'm building up to is to the Quaternion representation of rotations in 3D. And I will also explain you the slurp interpolation of rotations as we are at it. And then explain how this is important in rigid body physics and kinematics. Okay, so first we can do Quaternion conjugation. That's really a generalization of a complex conjugation. So what happens, I just flip the sign on all of the imaginary parts. So I do minus x, minus y, minus z. It's an analog of complex conjugation. Now using that, I can define a Quaternion norm. So norm will be just the square root of q conjugate q. So here I denote the conjugation with a little star. And then the norm would be exactly the same thing as if I looked at the Quaternion as a 4D vector and took it out of the norm. And if I say that a Quaternion is unit, that means that the norm or length of the Quaternion is 1. The unit Quaternions will be particularly important for us because those are the ones that correspond to rotations. This will be the constraint that will reduce the 4 degrees of freedom of Quaternions to 3 degrees of freedom of rotations. And there are some elementary properties you can prove. It's not too difficult. So if you want to, again, understand this a little bit better, you can write out the exact formulas and prove that's true. So the norm of P times Q, the times is a Quaternion multiplication here, is equal to the norm of P times norm of Q. So this would be just a real number multiplication, scalar multiplication. Okay. I guess I'm like obsessed with types just to make sure that it makes semantically sense. If you conjugate P times Q, you get the same thing as Q conjugate P conjugate. And here there is also Quaternion multiplication between the two, the operation without any symbol to it. Well, and this is quite obvious. If P is unit, well, no, if P is unit, then P conjugate P is the same as P conjugate. In both cases, it's 1. But the funny thing is this 1, I'm looking at it as a Quaternion 1 as opposed to real 1. It's like, again, just like a type difference, if you think about it. But in like quaternion 1 means really like a quaternion with 1, 0, 0, 0, right? As opposed to just real 1, which is just 1. It's silly semantics, if you will, but it's a little bit different. Okay, here is. Oh, did I? Yep.
Isn't that the same as the transpose?
Not really.
Seems to have similar properties.
Well, no. The deal about the quaternion conjugate is that it negates the complex parts. Sorry, the complex. So the x, y, and z, you can be calling them like the imaginary parts, and it negates them, right? Transpose doesn't do anything like that. Transpose only changes from row to column. We don't do anything like that in quaternions. So yeah, the conjugate does more than just transpose. Oh yeah, I see that you, this is probably why, right? Because if the thing is that, okay, here there is a quaternion product between them, okay? So this is not completely obvious. You would actually have to show that the vector part vanishes if you do this. That's basically what I said here. Again, it's a relatively simple matter. You just carry out the multiplication using this rule or even using the basic quaternion rules, and you will see that the vector part does vanish. Okay. Yep.
We often represent complex numbers as its magnitude times e to I theta. Is there some exponential form representing quaternions?
Well, that's an excellent question because this is exactly my next slide. So that is an excellent question indeed. So let me just start by repeating what you said, actually. So Euler's identity for complex numbers, which you should all know, what does it say? It says something like this. If you have a complex number, oh, I apologize for these stripes. It's something with our color printer. If I have a complex number z, then I can write it like this, like the norm of z times e to I alpha, or equivalently, norm of z times cosine alpha plus I sine alpha. That's for complex numbers, right? You should all know this. This is a complex exponential, and this is just if you expand it using cosine and sine. And I is our complex unit. And this exactly, that's what you were asking, right? And that's exactly generalizes to quaternions. So in quaternions, so this is for a unit quaternion. And for non-unit one, it works the same way too. So you also have the cosine alpha and sine alpha there. But this R here will be a quaternion with 0 scalar part, okay? So this R, maybe I should write it specifically. R as a quaternion will be something that has 0 for the scalar part, Rx, Ry, and Rz. Okay, this Rw would be equal to 0 because the scalar part is basically here. And it's true that any quaternion can be written can be written like this. And if the quaternion happens to be unit, then of course the norm is 1, so I don't need this part here. So I only do this cosine alpha plus R sine alpha. And what this is useful for, this will be useful for slurp later, but we can start by defining the power, and let's just do unit quaternion. If it was not unit, it would be a simple generalization of that. So the power means that you just multiply whatever is in the argument here. So you just essentially multiply the angle alpha there. So if I do the power to t, I will just get cosine t alpha plus R sine t alpha. I guess this will make a little more sense after I connect it to rotation. And that's what happens here. So this is really why quaternions do matter in graphics and physics or physics-based simulation. Okay, because quaternions represent in a very elegant way 3D rotations. So maybe we should first talk a little bit about 3D rotations before we say how quaternions represent them. So you know that every 3D rotation is can be explained as a rotation about an axis with some angle, right? It's actually an interesting exercise to think about why does every 3D rotation have an axis? Or first of all, what actually is an axis of rotation, right? So if I have a rotation, so let's say I have an arbitrary rotation R, an element from SO3, right? So I know that RTR is identity, and I know that the determinant of R is 1. So axis of rotation means that it's a 1D subspace invariant to the rotation. Did it make sense? Invariant 1D subspace. In symbols, if A, a 3D vector, let's just do this. A is an axis of rotation. If and only if, by definition, RA equals A. If the rotation doesn't do anything to it. That's what axis of rotation is. It should also be, it must be a non-zero vector, otherwise it would be trivial. Or we could just say it's unit length to make it clear. Do you know how to show, that's an interesting exercise, how to show that every rotation in 3D has an axis? That's an interesting thing that does not happen in 2D, right? In 2D, the axis of rotation is just given, right? That would be the z-axis. There is no discussion about the axis of rotation in 2D. In 3D, there is. Do you know if I give you a rotation matrix, you know how to find an axis of rotation? Okay, so let me explain that. Actually, it will be also useful linear algebra refresher, which I meant to do, but this will serve as a quick linear algebra refresher. The trick is to look at eigenvectors of R. So let's remember what are eigenvectors. So what are eigenvectors? Eigenvectors are vectors x such that Rx equals lambda x. X must be non-zero, so it's a valid eigenvector. And lambda is, in general, a complex number. Okay, so if I have a lambda and x, which satisfies this equality, and the x is non-zero, and the lambda is complex, then I say that x is an eigenvector of R, and lambda is an eigenvalue of R, right? I hope you all know this. And you probably also remember the standard linear algebra mumbo jumbo. How do we derive the formula for eigenvalues, right? So we just put this. I don't want to do all this linear algebra stuff here. This is the standard thing. So for lambda to be an eigenvalue, this equality must be true. Okay, the determinant of R minus lambda I must be 0. I hope I'm just like boring you now by saying things you already know. So that means if I write it out explicitly, that would be R11 minus lambda, R21 minus lambda, R3, oh, what am I doing? There's no lambda. R12, I guess I have to be more careful even though this is simple stuff, R32, R13, R23, R33 minus lambda, okay? So determinant of this matrix, that's the R minus lambda identity, must be 0. Okay, so if I look at it in terms of lambda, lambda is the unknown here. R's I have given to you. Okay, those are some unknown numbers. So what this is a third degree polynomial. Or third order, what is the right thing to say, order or degree? I never remember. Looks like this, right? And what I'm doing, I'm setting this to 0. So if lambda is an eigenvalue, it must be a root of this polynomial. Okay, and what we also know, that's the fundamental theorem of algebra or something like this, which is neither fundamental nor of algebra, but nevertheless it's true. And it says that every polynomial like this of order 3 has 3 complex roots. They are there, and it's easy to see that if lambda is a root, then also the lambda conjugate is a root too. Is also a root. That's quite easy to show. So because we are in dimension 3, that means there has to be at least one real root. Does it make sense? Because, I mean, I have 3, right? I have lambda 1, lambda 2, lambda 3. But if one of them, let's say lambda 1, must be equal to its own, oh wait, I noted like this, to its own conjugation, well, that means that lambda 1 must be real, right? There's no other way it could be equal to its own conjugation. And then lambda 2 and lambda 3 can be different, right? Because lambda 2 might be the conjugate of lambda 3, but that's okay. But because we have an odd dimension, we are guaranteed at least one eigenvalue which is real. That's the point here. Well, so let's assume, without loss of generality, it's the lambda 1. So let's assume that lambda 1 is real, like here. And let's say that its corresponding eigenvector is x1. Okay, so that means that I have Rx1 equals lambda 1 x1. That's from the eigenvector definition. And let's take a look at the norm of Rx1 squared, whatever. What is that? That would be x1 transpose R transpose Rx1. But RTR is identity, right? So this is just the norm of x1. Okay. Now I know that Rx1 is lambda 1 x1, so this is also equal to the norm of lambda 1 x1 squared, which is, because lambda 1 is just a real scalar, this will be just lambda 1 squared, the norm of x1 squared. Okay. Now because these two things are equal, this implies that lambda 1 squared, so lambda 1 must be plus or minus 1, right? No other possibility. But I also know that the determinant of R is 1. And what is the determinant of R? The determinant of R is the product of the eigenvalues. This is really like a linear algebra exercise. I hope you are enjoying it. I am. Lambda 1, lambda 2, lambda 3. So this is equal because lambda 2 and lambda 3 have to be complex conjugate pairs. One is the conjugation of the other. This must be the square norm of lambda 2. That means something that's non-negative and real. Okay? And if the determinant R is 1, that's our assumption because that R was a rotation, well, that means that lambda 1 can only be 1. It cannot be minus 1. So this minus 1 cannot happen. Okay? So this is a long way of saying that basically this one must mean that Rx1 equals x1, and guess what? That means that x1, the eigenvector corresponding to the real eigenvalue, that's our axis of rotation. Axis of rotation is sort of cool because once you have the axis, was that somewhat clear? I went sort of, I don't know if I went too fast or too slow. Probably too slow for someone and too fast for someone else. But I think it's all correct. Anybody wants to ask a question? If not, then let me just explain. Once you have found an axis of rotation, then you have basically understood a lot about the rotation because let's imagine this is a 3D drawing. This is an axis of rotation, and I can find two orthogonal directions to the axis of rotation, some B and C. And what I know is that the rotation is a 3D transformation, and here would be the origin, 0. The rotation leaves A alone. Okay, and if I have any vector here, if I have arbitrary vector, I don't know, P, if I decompose it into a component in R and into a component in the BC plane, so the rotation does not touch the component of my vector in the A direction. Okay, and what happens in the BC plane? Do you see like the mental picture you should have here? There's an axis like this. There's a plane orthogonal to that axis. The rotation doesn't do anything to the axis of rotation or anything that's parallel to it. But it does something in the BC plane, right? In the plane orthogonal to the axis. What does it do there? Something very simple. 2D rotation, right? So the 3D rotation essentially, after you have found the axis of rotation, the 3D rotation essentially reduces to a 2D rotation. Okay, so now I think we are ready to go to Quaternion representation of rotations. Oh, by the way, in 2D you can do similar thing with complex numbers. In 2D it's like sort of boring because there is only one axis of rotation, and that's this, right, pointing out of the plane. And also in 2D the rotations are actually commutative. That's why complex numbers are commutative, and in 3D they are not. Anyway, so let's explain this. This is very important. So as I said, for every rotation in 3D, so now we actually have a proof that there always exists an axis of rotation. The length of the axis of rotation doesn't matter as long as it's not 0. 0 would not be cool, but as long as it's not 0, you can divide it by the length and you can just assume the axis of rotation is unit, right? That doesn't matter. And there is an angle of rotation. That's basically the angle of the 2D rotation. After you do this, then we are left with a 2D rotation that has some angle. That's my angle alpha. That angle can be 0 if it's identity, right? Or it can be anything. And here is the thing. Here is how Quaternions represent rotations. So what we're gonna do is this. So take an arbitrary. Oh yeah, take an arbitrary 3D vector, and we can represent it as a quaternion. As a quaternion with 0 scalar part. We have 3 numbers in a 3D vector, so we can just put them as coordinates with multiplying I, j, and oh, sorry, it was supposed to be k. Okay. The q denotes the set of quaternions. Now we get, so we have an axis of rotation A and angle alpha, and we define a unit quaternion. You can very easily prove that that's its unit, by the way. And it will be cosine of alpha half. Interesting thing, this half. I will have more to say about that later. And A, so A, I assume, again, was converted like this to a purely imaginary quaternion times sine alpha half. Okay? So if we take this unit quaternion and we do this product, if we do Q, quaternion multiplication V, quaternion multiplication Q conjugate, we get V prime. And again, you can prove that that will be a quaternion with 0 real part. Okay, just like the V. The V is a quaternion with 0 scalar parts, scalar or real part, doesn't matter. The same thing, V prime also will have 0. So we'll only have these components. Oh, here is the same bug, probably copy and paste mistake. So there will be 0 scalar part, and there will be some general xy prime, x2 prime, and x3 prime parts. Okay, the purely imaginary components of a quaternion. If I convert it to a 3D vector, x1 prime, x2 prime, x3 prime, guess what the x prime is? It's exactly a rotation of the x about axis A with angle alpha. Let me give you a second to reflect on that. So what happened here is that this funny product, which some people call it the sandwiching product. I don't know if they call it like that because they are hungry or because this looks like a sandwich, Q and Q star, Q conjugate here. This double product of with quaternions, what it does, it exactly implements a 3D rotation. It's exactly the same thing as if you converted this A and alpha to a rotation matrix, and apply the rotation matrix to X. So if you let me write it like this, if you did a rotation matrix M, A and alpha, you multiply with X, you would get exactly the X prime. It's a cool exercise to actually derive it. You just like turn the crank, write down all the algebra. Takes a while, so I'm not gonna do it, but you can do it for yourself if you want to assure yourself of this. So basically what we can conclude here is that the quaternion Q represents a rotation about angle alpha and axis A. And it represents it in an interesting way. Through the sandwiching product, it actually executes or computes the rotation. Okay. But there is a very interesting catch to it. It seems now, so let me, in terms of groups, I have the SO3 group, that would be the matrix group of rotations. And if I say that Q1 is a group of unit quaternions, that's also a group. My hand is like shaking to write that they are isomorphic, that there is that they are basically there's a one-to-one mapping between rotation matrices and unit quaternions. Okay, except that it's not true. Okay, why is it not true? Well, there is one catch which some people are not aware of, and then they are surprised that their quaternion code isn't working, and this is exactly why it isn't working. It's because both quaternions Q and minus Q, they believe it or not, they represent the same rotation. So the mapping from rotation matrices to quaternions is not 1-to-1, but it's 1-to-2. Both Q and minus Q, they will give you exactly the same 3D rotation. For example, 1 and minus 1, if I look at them as quaternions, meaning that the 3 other components are zeros, believe it or not, they both represent the identity rotation. So rotation about angle 0, if you will. Why is that? The reason is quite simple, right? If you look back at the sandwiching product, certainly multiplication by a scalar commutes with everything. So if I use their minus Q, and of course minus doesn't do anything to conjugation, so here I can just pull out the minus, and the minus cancels out. So if I do minus Q times V times minus Q conjugate, I get exactly the same as if doing Q, V, Q conjugate. So it really cancels out. That's an interesting property of this double or the sandwiching product. And that has real consequences you need to be aware of when you are coding up anything with quaternions. Otherwise, you might be very surprised. I will get to that. So first, let me notice one interesting thing. So now we know that unit quaternions represent 3D rotations, and it gets even better than that. Quaternion multiplication corresponds to composition of rotations. You can compose rotations, right? In matrices, you just multiply them together. Turns out in quaternions, you also just multiply them together. Why? Because if we have our V prime, like here V prime was V rotated by Q, now we know that the Q does a rotation, right? If we rotate it by another quaternion, P, we can write it like this. So we do another sandwich with P and P conjugate. And if we just recall the one rule that Q conjugate P conjugate is PQ conjugate, then you just see that this is V sandwiched by P times Q, okay? So in other words, P times Q, or the times quaternion multiplication, means that this is a quaternion that corresponds to the composed rotation, okay? If instead of P I put there Q conjugate and Q is unit, I will see that this disappears, and from this I can conclude that the conjugation gives me what? It gives me inverse rotation. If the quaternion is unit, if Q is unit, then Q conjugate corresponds to inverse rotation. I guess that's what's written here. And of course, 1, again, understood as a quaternion, so 1, 0, 0, 0, corresponds to identity. And so does, by the way, minus 1, 0, 0, 0, right? Like we wrote here. So if you want to know how to convert a quaternion to a rotation matrix, again, you can derive it by yourselves. Essentially, you just all you need to do is to expand this formula, have symbolically, and convert it to this expression. And what you will get in the matrix are these values. And this is how you can convert a quaternion to a rotation matrix. Here you can also see why changing the sign of all the components. So if I replace w with minus w, x with minus x, y with minus y, z with minus z, then because they all occur, they are all multiplied together, so the minuses indeed cancel out, just as I said before. The conversion back from matrix to quaternion, usually you don't have to implement it because you usually use some library which already has that implemented, but I have seen bugs in there, so if you actually know how that works, that can't hurt. The conversion back basically means you have a matrix and you have to extract the x, y, z, and w from that. So you basically just need to invert this. It's also quite simple, you just need to be careful not to divide by 0. That's I think what already Ken Shoemake figured out in his paper when he has these, where was it? Oh, the other Theorem. When he has these, when he's checking which of them is big enough so he can divide by that. It's just like a safeguard so you are not dividing by 0. It's also a simple closed form expression. Just need to be slightly careful not to divide by 0. Okay, what next? So one standard application of quaternions is interpolation of rotations. It's not strictly speaking physics, but as we are at it, I can explain it as well. That goes to spherical linear interpolation. Do you know SLURP? How does that work and how does that relate to quaternions? So let me just explain that quickly. So if we have two rotations, we want to interpolate between them. So interpolate means we want to find an intermediate rotation for a parameter t going from 0 to 1, such that for 0 we start at r0, at 1 we end at r1. We get a rotation everywhere in between. And finally, we would like the angular velocity of an object transformed by rt to be constant. In other words, if I'm interpolating in rotation, I want nice constant velocity as opposed to like faster and slower, something like that. So you probably all know that just interpolating rotation matrices linearly is not a great idea, right? That's because that does not give you a rotation, right? Already the number 3 is violated, right? Because interpolating orthonormal matrices, already the orthonormality will be violated, right? It turns out that linear interpolation of quaternions actually works surprisingly well, assuming you took care of the minuses, of the antipodality. So if you do this, if you convert the two rotations to unit quaternions, and then just interpolate them linearly, and then normalize them to length 1. Okay, so normalizing them, if we just look at them as 4D vectors, that's nothing difficult, just divided by the length. What does it mean? There is an easy way to think about it geometrically. Maybe I need to explain that a little bit better. So the Q1 is a set of all quaternions, all unit quaternions. Okay, so that would be my W, X, Y, Z, such that W squared, X squared, Y squared, Z squared equals 1. What is this set geometrically? What is the set? What is this? It has a name. The set. So this is our group, really, right? But right now, I'm just concerned about the geometry. Yep.
Are you talking about like what group it's part of, or I'm slightly confused.
Well,
would it be like the standard, the unitary group, or?
No, I'm just like, you know what? Let me back off a little bit. Let's take a look at this. Xy x squared plus y squared equals 1. What is this geometrically? That's a unit circle. That's right. What if I do this? X, Y, Z. How do you call this? That.
Then it will be S3.
This is S3, I believe. This is S2.
First one is S3.
So there will be S4, I think.
No, it will be S3.
Oh, well, I guess maybe you're right. Oh, yeah, I don't really remember. Yeah, how do we call this? We can call it a hypersphere. So it's a 3-dimensional sphere living in 4 dimensions, right? Those are the 4 dimensions. There is one constraint which cuts out a 3-dimensional hypersphere. So maybe you're right. It's called S3. So how to actually visualize it, I do not know, but we can just think about the standard sphere, which is easy to visualize, just a ball, right? And just carry over our intuition. So why I'm mentioning this in this context is because we can understand the linear interpolation of quaternions if we realize that this is just a hypersphere. Because what you want to do here, so if what you can imagine is happening here, if we have 0 here, Q0 here, and Q1 here, then I'm basically slicing the hypersphere with a plane passing through 0, Q0, and Q1. In any dimension, any 3 points on any 2 vectors generate a hyperplane, just a 2-dimensional subspace. And if I slice the hypersphere, slicing meaning intersect to be precise, if I intersect the hypersphere with this 2-dimensional subspace, then I must just get a circle. Okay? And on the circle, what the linear interpolation of quaternions does, well, it just draws a line between Q0 and Q1, and this divide by the norm that just normalizes it, right? So for example, this would be my Q.5. That would be right here. And when I normalize it, I will project it back to the unit hypersphere, and I will get here. Okay? So you can see that this interpolation satisfies the first 3 properties. Now we indeed have a rotation because we normalized. We have a unit quaternion corresponds to rotation. What it does not satisfy is the condition number 4, because as you can probably see, if I'm going with constant velocity here, constant speed here, I will not get a constant angular velocity here, right? First I will go a little bit slower and then a little bit faster, but just by a little bit. So in graphics, this is usually a pretty good method of choice if you took care of the antipodality, which I will get to in a second. If you really want constant angular velocity, then what you want to do is SLIRP, spherical linear interpolation. And that's defined like this. So here is where we need the power of a quaternion. That's what I explained in the context of Euler's identity for quaternions. Because what the power does, the power essentially says interpolate the angle. Okay? Some more to that? No. Maybe it would be worth mentioning, so what does this formula mean? This is the formula for spherical linear interpolation, where P is one of the rotations, represented as unit quaternion. Q is the other rotation, also represented as a unit quaternion. So what is P conjugate Q in English? So I mentioned that if P is unit quaternion, then P conjugate means the inverse rotation, right? And if I multiply it back with Q, or you know what, maybe this might help. So what if P is identity? What is happening there? Yep.
Is P times P conjugate transpose just identity?
P times P conjugate.
Transpose just identity.
Oh, this is not transpose. This is to the power of T.
Okay.
Sorry. Yeah, this is. Let me bring up that Where is he? This is the t. The t is my interpolation parameter. That's a real number. It goes from 0 to 1. And this q to t, or in this case p conjugate q to t, that means raised to the power of t. So that's the quaternion power. And the way we do it is exactly using this formula, right? If we convert it, if we know the alpha and the angle, then the t just enters, to multiplies the angle. That's why it's a constant angular velocity interpolation, because the t basically means interpolate the angle there. But back to my original question, what is p conjugate q? I have some good explanation for that. P conjugate q is basically the relative rotation between p and q. Okay, in matrices it would be the same. If I have a rotation matrix R1 and R2, then R inverse R2 would be the relative rotation between R1 and R2, right? The easiest case you can think about is if P is identity, then this reduces to just Q to the power of T, right? Which means exactly just multiply the angle of rotation. So if I'm rotating, if I'm interpolating some target rotation from the identity, so I clearly start with rotation with 0 angle, right? So I start with 0 angle, and I progressively increase the angle, linearly increase the angle until I get to my target rotation. So this is spherical linear interpolation. And here is the important catch, which I want you to be aware of, because otherwise you can get some weird behavior. So I mentioned before that minus q represents exactly the same rotation as q, okay? So that's, some people consider it the weirdness of quaternions. It's what happens if you use minus q instead of q? You might think that nothing happens because they really represent the same rotation, right? Let's dribble the sun. Not sure what to do on that. What do you think that happens if I use minus q instead of q? So if I convert minus q to matrix, exactly the same matrix as if I convert q to matrix. Doesn't make any difference there. But if I do slur between p and q and between p and minus q, I can get a dramatically different result. If you don't believe me, just try it in your favorite Quaternion library, unless it does some tricks behind the scenes. You will see a dramatically different result.
Does the correspond to two different geodesics along the sphere?
Yes, exactly. To the exact opposite one. So let me explain that in some more detail. You already have the right idea. So how do we explain that? So the relative rotation between P and Q, that's the P conjugate Q. That's essentially, that's the part we are interpolating, right? So if you look at the scalar part of P conjugate Q, here I need to bring up my, I mean, I remember it, but maybe you don't. So I need to bring it up. So if I do P conjugate Q, I look at the scalar part, because the Q was conjugated, that means its vector part was negated. So here I will get plus, okay? So what that means, the scalar part of P conjugate Q will be WPWQ plus the dot product of RP and RQ. Remember, this is a dot product. So this is nothing but a 4-dimensional dot product between P and Q. If I look at the quaternions, unit quaternions as unit for the vectors, the scalar part of P conjugate Q is exactly the dot product of P and Q, okay? Yeah, if I'm looking at it as 4D vectors, then the dot product, as you know, is the cosine of the angle between them, right? That's linear algebra first class, at least in my course. And if you connect it to what we know about quaternions, from the Euler's identity here, here, not Euler's identity, but the connection to 3 rotations. So if I have a quaternion and somebody asks me what is the angle of rotation of the quaternion, I just need to look at the scalar part, and I know that the scalar part is the cosine of the angle of rotation divided by 2. Okay. Well, because this already is, the dot product already is the cosine, then I know that the angle of rotation of the relative rotation is exactly 2 sigma. It's 2 sigma because of this half here. Here is where this half becomes important. Okay. So the angle of rotation we are interpolating here is 2 sigma. And imagine what happens if we use minus q instead of q. If we plug there minus q instead of q, then we get the negative dot product, which is minus q dot product q, which would be minus the cosine of sigma, right? Before we had a cosine of sigma here. Now we have a minus cosine of sigma by the standard trigonometric identity as the cosine of pi minus sigma. And if I multiply by 2, I get 2 pi minus 2 sigma. Okay. So, for example, if sigma was 60 degrees, that means that the relative rotation between P and Q was 120 degrees. But if I interpolate instead of that P and minus Q, that means I am doing a rotation of 240 degrees in the opposite direction. Okay? And this is why it matters a lot, because you probably want to be interpolating the shorter path, not the longer one, right? But if you just pick randomly between Q and minus Q, you don't know which of these two paths you are taking until you look at it, and when you look at the long one, you might be disappointed. There's a cool way to look at it on a slice of the Quaternion sphere. So if I take my hypersphere of Quaternions and I intersect it with a 2D plane, the 2D plane where the two Quaternions P and Q lie, then I certainly get a circle. And if it's a situation like before, if the relative rotation between P and Q was 120 degrees, then on Quaternions I will get an angle between P and Q which is 60 degrees here. And if I look at P and minus Q, I will get 120 degrees in the opposite direction. Okay. So if I'm interpolating between P and Q, I'm interpolating this way. And if I'm interpolating between P and minus Q, I'm going this way. Okay. Ultimately, I get to Q or minus Q, which both represent to the same orientation. Both correspond to the same orientation. That's like here, right? I'm rotating a Christmas tree or whatever. Either way I rotate it, I get to the same orientation. I just get there with a different path. Okay. And what we typically want in graphics is to take the shortest path interpolation. And because we don't know if we are using minus Q or Q, like how do you know if there is minus or not, right? You can always multiply by -1. There's no way to tell. So what you can do is to select the sign such that the dot product between P and Q is non-negative. And that's how you make sure you are taking the shortest path when interpolating between two rotations. And by the way, once you have done that, then the linear interpolation of quaternions is just fine, because the most you can be interpolating, the most extreme case is like this, that one is here and the other one is here. So at most you are interpolating like this. So the linear interpolation only is this much inaccurate, okay? Because if you were going to interpolate to here, you're not gonna do that. You're gonna flip here and interpolate these two instead, okay? So this thing, this fact that both Q and minus Q represent the same rotation, that's a very cool thing. That's the one thing I would like you to remember from this lecture. This is called the double cover property of quaternions. And believe it or not, it actually has real world consequences, quite interesting. Have you heard of Dirac's belt trick? Does anybody have a belt? Or I guess I have a belt, I can just use it. I will show you the trick on a belt. It's about interpolation of rotations. If somebody has a belt or something like this, it's okay, I can use mine. I'll need somebody to hold it. Do you want to hold it? Maybe here. So let's see if I still remember it. So what matters is the orientation. Okay. So let's assume this is identity orientation. Okay. And this I can rotate. So this would be 180. This would be 360. Okay. And now that the belt, unless I want to cut it, it will be continuously interpolating the rotation. Okay. So here will be, I don't know, 10, 20, 180, somewhere in the middle, right? I can shift it back and forth, right? And now I can be playing with the belt. I can be doing continuous transformations with the belt. Right? I can shift it like this, so most of the interpolation is now happening at the beginning, or I can shift it like this, so like now it's not doing anything for all belt, and then very quickly goes back to 360. Okay. So if I give it 360, I can be doing all these things, but I can never get rid of this. But once I get to 720, so I got to 540 and 720, and now there is a trick I can play. That's the direct belt trick. Let's see if I can get this right. If I do this, and the rotation disappeared. It's like a magical trick. And you see, this is perfectly straight. This is identity. And I can explain you what happened on Quaternions. This is very cool. I can explain you what happened here. So let's imagine this is my hypersphere of unit quaternions. Here is my identity. Okay, here would be somewhere would be the 0, the origin, that doesn't matter. So if I twisted one end of the belt by 360, I got here to -1. Okay, and I got some path that interpolates, smooth continuous interpolation. So one end of the belt was at 1, the other one was rotated by 360. Okay, at -1. And here I had a smooth interpolation between that, right? And I could play with the belt all the way I want, and I could like create some different path there, right? Or even change the speed, like when I like I was not doing anything there, and then went really quickly to -1, right? I could do any continuous transformation to that curve, right? Now the cool thing happened when I did. Let me do another picture here. When I actually did a 720 degrees rotation to it, what I created was a loop there, okay? And then making a continuous transformation of the loop, I could shrink it to nothing and get identity on the belt. You can play with your own belt and realize that this is actually true. So that's the Dirac's belt trick. And that concludes the Quaternion talk, unless you have any questions. Oh, this thing? The Dirac belt trick? Yeah, okay, sure. So basically I have a belt, okay. And I say I fix the orientation of one end. I fix it to the Quaternion identity, okay? And what I did then I progressively rotated the other end of the belt. And as I was rotating it like this, you can imagine I was like going, for example, like this. Like here I got to 180, right? And I kept rotating, right? So ultimately I got here to -1. So that was 360 degrees rotation, yeah? But the point is that the belt remembers the rotation in between, right? That the belt cannot forget the 360 degrees rotation. It's in the body of the belt. And no matter how, if I do continuous transformations, if I cut the belt, this would be discontinuous transformation, I could get rid of it. I don't want to cut my belt, I still want to wear it. So if I want to do just continuous transformations, there is no way to get rid of it. I can just change the distribution of the interpolation. So on Quaternions, it corresponds to a path that connects 1 and -1, the two antipodal points. And if I'm continuously transforming it, I cannot tear it away from -1. But I can change it a lot, right? Now, once I kept rotating to 720, I got to 540 at some point, and then I continued to 720. Then I actually created a loop on the Quaternion hypersphere. And then by making a continuous transformation of that loop, I could just make it disappear. It's not that difficult to make it disappear. It's just a cool thing. I heard it has some consequences in quantum physics, but I'm not exactly sure what those are. I haven't studied it in detail. I just think it's a little cool little thing. So what I want you to remember is that the Quaternion hypersphere represents rotations twice, basically, right? the half sphere already has all the rotations, and the other half has the same rotations once again. Yeah, so that's the take-home message. Any other questions? Yeah.
Can you look at a quaternion in its complex form and tell which direction it will rotate in? Like for example, when we have Euler angles, we kind of have an intuition.
Mm-hmm.
It's counterclockwise or clockwise. How do we?
Oh, that's easy. You just convert it to the quaternion. Yeah, which direction it will rotate. That's clearly visible from here, right? The quaternion is this. So this is an axis times unit axis times the sine of the angle. So this will be telling you, if you normalize it, this will tell you the direction. I guess you need to also look at the cosine. From this, you can figure out the sine of the angle of rotation that will tell you which direction is it rotating, if that's what you were asking about.
Yes, but if the quaternion was represented in a complex form, then I'd have to come to this form for knowing the direction.
I'm not sure what do you mean by complex form.
Which
Oh, like the
four, when you had the IJK and the W.
yeah, but this is still the same thing, right? This would be the W, and the X, Y, and Z. That's this, right? This is just saying what. Maybe I can write it explicitly. If this is like A1 sinus, not sinus. That would be like the X. A2 sine alpha 2. That would be the Y. I guess that's a good question. Sine alpha half. That would be my Z, right? And my W would be, of course, the cosine alpha half, right? So the things you have there, they are this, right? It's just an interpretation of the numbers. All right. So let's see if the recording worked this time. I'll stop it now, unless there are some more questions.